am Mr. True. In this video, we're going to be talking about inference for regression, specifically linear regression t-tests and confidence intervals about the slope of the regression line. Is there a linear relationship between two variables? Well, if the slope of the regression line equals 0, then the answer to that is no. There is no relationship. If the x-axis is changing and the y-axis is not responding, y is like, I don't care what x is doing, I ain't changing. So there's no linear relationship there. And of course, we are talking about, in intro to statistics, we are talking about linear relationships. There's other types of regressions you can make, quadratics, cubic regressions, and so on. We are just talking about linear regression. If there is evidence that the slope is not equal to 0, then we will conclude that there is a relationship between the explanatory variable, the x-axis, and what is on the response variable, or the y-axis. And remember that we are studying the predicted y values in response to x. So we're going to be looking at, again, it's y hat equals a plus bx, not x hat. We do not predict our x values, we are predicting y values from a response of x. So we have 4 checks that we need to validate for doing linear regression t-tests or talking about making confidence intervals for the slope of the regression line. Some of them easier to check than others. Sometimes we just need to state that we know that they exist. We have repeated responses of y are independent of each other. We've always needed independence with all of our significance tests, and remember it's the y values that we're predicting, not the x. So we only need independence. It would only make sense to talk about independence in those y variables. The mean response of mu y has a straight line relationship with x. Of course, we can't run a linear regression t-test if the pattern's not linear. So we have mu y equals alpha plus beta x. This is our true regression line that we're trying to predict with our calculator when we do a linear regression a plus bx, where we're using b, lowercase b is our estimate of the unknown parameter of beta, or the slope, and lowercase a is an estimate of the unknown parameter alpha. So when we look at a scatter plot, that is a sample, and the slope and the y-intercept that we get are estimates of the true slope and the true y-intercept. And of course, as far as checking for a linear pattern in a scatter plot, we've got our old friend, the residual plot. And depending on your calculator, different steps, but you will need to make the scatter plot, then tell the calculator to make a regression line, and then once it's calculated the regression line, you can look at the residual plot and validate that the pattern is indeed linear. Remember, your scatter plot, you want depending on the zoom of your window, you either want no pattern at all in your residual plot to validate linearity of your original scatter plot, or you want that horizontal band, which would show that your points are consistently and evenly distributed above and below the regression line that you put through it all the way through the pattern, thus the pattern was linear. The standard deviation of y, which is going to be identified here with sigma, the standard deviation of y, sigma, is the same for all values of x. Now, what does that mean? Well, I've got a couple of pictures down here for you. As you go along the x-axis, you want the spread of your residuals. You want the spread of the actual y values. Residual is y minus y hat, the difference between the real y value and the expected y value. That's what you get from your regression line. You want a nice even band or elliptical type shape around the entire regression line. What you don't want to see, and it doesn't matter if it's getting bigger or smaller, but you don't want to see your, this is not an x variable, it's like you don't want to see this. As you go along your independent, or explanatory axis, the x-axis, you do not want to see the variability in the y-coordinates changing along that x-axis. You do want the standard deviation of y to be the same for all values of x. So all along that x-axis you want to see a nice even spread of points along your regression line. You don't want to see an example here where the spread is increasing as the x values increase. And of course you wouldn't want this to be decreasing. It doesn't matter what the pattern is. You want those standard deviations to be the same along all of those x values. We got one more condition. Let's take a look at that. Okay, so we have our fourth check. For any fixed value of x, the response y varies according to a normal distribution. It's possible to make histograms with residuals if you have enough data. A lot of times in the textbook and on the AP exam, they don't really give us enough data to actually check for this normality idea. So you just have to state it in your assumptions or your conditions that you have to be aware that the y values are varying in a normal distribution with x. Kind of difficult to check, and a lot of times with our textbook questions, we won't really be able to. Just state that we know that it's a condition that must be met. Remember, when you collect data and display it in a scatter plot, you were looking at a sample. There is variability in the slope b, lowercase b, and the y-intercept a. That's what I mentioned in the previous screen, that a is a estimator of alpha and lowercase b is an estimator of beta. That, you know, when we look at a scatter plot, it is only a sample, and there is variability in the slopes and the y-intercepts. We haven't really discussed that in our Intro to Statistics class, as most of our work has not been dealing with two variable data. We just, you know, made scatter plots and drew regression lines and checked for linearity with residual plots, and, you know, described what we saw in the pattern. This is why we need to say there's on average, a linear relationship between y and x, or the regression line between y on x. Standard error of residuals about the least squares regression line. What is the standard deviation of the residuals? Y minus y hat. Well, s is equal to the square root of the summation of y minus y hat squared over n, the number of points in your scatter plot. This estimates sigma from the third condition that I said, that standard deviation of your y values along all values of x needs to be consistent through the entire regression line. Your calculator will give you this when you do a linear regression t-test. The standard error of the slope, older calculators would not give me this. My new TI Inspire, when you do a linear regression t-test, will tell you the standard error of the slope. But if you're doing these problems on a test, a lot of times, again, they will give you the Minitab output, which will tell you the standard error of the slope of the regression line, which is s, this value up here, the standard deviation of the residuals, over the square root of the summation of x minus the mean of x squared. The standard error of the slope is all we're going to discuss in this video. The standard deviation or the standard error of the y-intercept we're not going to discuss, because a lot of times the y-intercept does not have a real-life application. So we're going to be interpreting the slope correctly with the proper definition of slope we'll mention in a minute, and setting up confidence intervals, you know, of the slope of the regression line, because that always has a real-life application or meaning within your word problem. Next screen. Bye. So we're going to discuss how to set up a confidence interval. Same as always, estimate plus or minus critical value times standard deviation or standard error of the estimate, and then our shading for significance tests. Confidence intervals for slope is b plus or minus t star times the standard error of b, or the slope. Let's not forget that we are dealing with a continuous random variable, and we're working with means, so we are dealing with t-score. You know, we don't know the population standard deviation for our variables on the x or the y-axis, for that matter, even though we are just predicting the y values from our given x's. So we are using t-star, and the degree of freedom for your significance test or your confidence intervals is going to be not n minus 1 but n minus 2, and the best way I can, you know, just describe that you to remember that is, well, there's two variables. There's one on the x and one on the y, because up until now for t-tests, your degree of freedom has always been n minus 1, but it's always been univariate data. Well, now it's bivariate data, and I'm not sure if that's the best explanation for that, but it's bivariate data, so it's n minus 2 instead of n minus 1. The slope is the average change in y per 1 unit of change in x. The definition of slope as being rise over run is great for algebra, when all you're doing is graphing lines that don't have any real-world context, but we do want to really actually know the definition of slope, which is average change in y per 1 unit of change in x. You're going to use that when you interpret the slope of the regression line. Once you set up your confidence interval, just like always with your confidence intervals, you're going to say, I am blank % confident but now we have in terms of slope. I am blank percent confident that y changes on average, or an average of blank units, blank number per 1 unit of change in x. Stumbling around that, sorry about that. But it is, average change in y per 1 unit of change in x. So when you do your confidence intervals, blank percent confident that y changes an average of so many units per 1 unit of change in x. Y-intercept often has, again, no real-life interpretation. You'll see that in the example that we take a look at. Significance test for regression slope. Well, again, if there's no association, we always set up H sub O as no association, no difference, no effect from the treatment. So we are going to be doing the same assumption here, and if we're assuming that there is no association, then again, the x is going to be changed and y is not. That means that we will have H sub O set up as beta is equal to 0, the population parameter for slope. And then, of course, we might be looking for the slope to be positive, the slope to be negative, or just simply, is there a difference? Is there an association? I don't know if the y variable is going to increase with x or decrease with x. I'm just looking at, is there an association at all? And that'll be your two-sided test. Let's get a look at our example. We will be looking for, with our example, a slope which is negative. Here's our example. Does a car's weight negatively affect miles per gallon? And indeed it does. I did, however, make up these numbers since I'm trying to make a video for the internet and I don't have any copyright issues. So, true statement, not true numbers, but shouldn't be very far from the truth. I've got 12 weights here, ranging from 2168 to 3,902 pounds. We have miles per gallon going from 34 reducing to 17, and it clearly does seem like the heavier the car weighs, the less efficient it's going to be, the more gas it's going to burn. Now, if we could just observe that and go, that looks right, we wouldn't need statistics. Even though I have kind of made this example rather obvious, we do need to run this through a statistical analysis. Now, with the raw data, I have displayed a scatter plot. I've got it properly labeled. I've got scales and labels on the explanatory and the response variable. I've been doing a lot of pre-calc and calculus lately, so I got independent and dependent variables on my mind, but we don't say that in statistics because it overly states the idea of the y being dependent on the x-axis, and dependence is extremely hard to prove. It takes a lot to prove in statistics. So let me go back to, again, explanatory and response variable. And our regression line is y hat equals 58.4 minus 0.01x. So our slope is that for, well, I'm kind of getting ahead of myself. I was going to do this in the previous, on the next screen, but for every pound of increase in the car, the miles per gallon is going to be reduced by 0.01. Now, as far as the y-intercept, how I told you how it doesn't normally have a real-life application, well, in this problem, the 58.4 would be the estimated miles per gallon of a car that weighs, 0 pounds, right? Okay, so that clearly does not have a real-life application in this problem. Since we are given the raw data, I have sketched or copied the residual plot that I got. It seems like we have one little bit of a tiny bit of an outlier somewhere, but I don't see that in my original scatter plot. And t-tests do have some resistance against non-normality, and nothing in here to me looks like an influential point. And it says just a sketch, so it might be off just a tiny bit copying what I had on my calculator. But I have some validation for later when I say that it appears to have a linear relationship. I can refer to the scatter plot to validate that conclusion that the original data was indeed linear. Don't look for just a high R or either a high R value or an R squared value to validate normality. I'm saying high, but R can range between -1 to 1. The closer your R value is to 1, the stronger your linear relationship is, but that is not a test for linearity. We need the residual plots to do that. Okay, now you might also see data given to you in Minitab output. So I only drew a portion of what might look like Minitab output in your test or textbook, but it'll be a table with 2 rows of data. It'll say coefficient, standard deviation or standard error, t-score, and p-value, and have a row called constant and a row called weight. So when you see the coefficient of the constant, well, when we look at a regression line and it's y equals a plus bx, what's with the x is slope, and the constant is a number that's by itself. So the coefficient of the constant is going to be our y-intercept. The coefficient of, and then that row with the actual name to it is generally going to be, I'm just saying that because who knows of some special case that could come up, but that's going to be your x-axis. So the coefficient of the weight is negative 0.01. Well, that's what we would get from our, a plus bx from our graphing calculators. The slope is negative 0.01. Now the Minitab output will give you the standard error of the slope and give you the t-score from the slope, and that is indeed actually what we want. When you do a linear regression t-test, we're going to be doing those t-tests on the slope. And so basically they've already done the calculation of the t-score for us, and they will have also given you the p-value. I'm going to show a video on how to do a linear regression t-test on both an 84 and a TI Nspire. Look for those. They're not up yet, but if you're watching this video, it should be up soon, if not already. And then we have in the lower left-hand corner of your Minitab output, S equals 1.596 in this particular case. That's the standard deviation for the residuals along the regression line. So that's what that's for. Linear regression t-test. Well, again, we set up significance test with no effect, no difference, no association. And no association between weight and miles per gallon is going to be that we have a slope equal to 0. And of course, we are going to be expecting the heavier cars to be less efficient. So the heavier the car, the reduced miles per gallon. We don't set up H sub O and H sub A after we look at the data. That would be based on the assumptions that you have before you collect the data, and that would make sense. The heavier your car is, the less efficient it is. So we are going to be expecting our slope to be less than 0 or negatively associated. And indeed, that is what we saw from our data. Conditions. The scatter plot shows a linear association. We will assume that the 12 miles per gallon readings are independent. So I didn't really give you any background to the data, so we're just stating that we need to assume that. And the standard deviations of miles per gallon are the same for all values of x. Now, with the residual plot, we can see sort of a horizontal band along that regression line, so it's safe to assume that that should be the case. Now, I'm throwing in that we need to assume that the 12 miles per gallon readings are dependent. The standard deviations of miles per gallon are all the same for all values of x. My textbook, and as I told you, we need to check for normality. We need to have that normality in a fixed value of x. We need to have the distribution of y values be approximately normal for all individual values of x. They don't actually throw that word into the condition checks in my textbook. So I'm going to add that those residuals need to have a normal distribution. It seems kind of odd my textbook said that it needed to be, it was one of the 4 conditions, but did not include that wording in the conditions of the linear regression line, the linear regression t-test. So, what I know is from the book that I'm teaching from, so I'm doing the best I can here with that one. With a degree of freedom of 10, there was 12 points in the scatter plot, so 12 minus 2 is 10. So with a degree of freedom of 10 and a t-score of negative 11.8 given to us by the Minitab output or doing the linear regression t-test with your calculator if you're given all the raw data, and a p-value of approximately 0, which again, we can just simply use a t-table to find that value. Our calculator will give us that value for doing a linear regression t-test, or again, it's in the Minitab output. There is very strong evidence to reject H sub O, and that, if we're rejecting H sub O, that the slope is equal to 0, then we're accepting H sub A, which is the slope is negative, and thus the increased weight in the cars reduce the miles per gallon. So that's how you sort of do a linear regression t-test. A lot of these questions do give you the Minitab output, so you're not really doing much. You're just, recognizing the type of test you need to set up. You're recognizing how you need to set up H sub O and H sub A. You're stating the conditions that you understand them, you know what they should be, and then you're interpreting, whether you're going to reject H sub O or fail to reject H sub O using the data that's in the Minitab output for you already or that you get from your calculator. I'm going to clear this off and give you a statement about or an example of setting up our confidence interval for this slope, and we'll call this video done. Woo! Here we go. Estimate the true slope of the regression line with a 95% confidence. Well, with the degree of freedom of n minus 2, we have again 10 as our degree of freedom. And looking at the t-score chart, t star, critical value for being 95% confident with a degree of freedom of 10, is 2.228. So, our actual observed slope, lowercase b, negative 0.01, I rounded it off, it's actually negative 0.0106, is our observed slope plus or minus the critical value times the standard error of the estimate, or the standard error of our slope. Thus, I get a conclusion. I'm 95% confident the true change in miles per gallon per increase of 1 pound. Well, let's just read what I wrote. I'm 95% confident the true change in miles per gallon per 1 pound increase in the weight of the car is between negative 0.012 and negative 0.008. And again, slope is average change in y per 1 unit of change in x. I'm Mr. True. Bye! Go do your homework.